Here you see the assignment number 4, number 6. You don't find yours, means you did not turn it in. Okay, I think I wrote it wrong in the email. Methyl acetate, not ethyl, methyl. How do we convert from non-separator into a single reactive distillation column? Lee Parton, BS graduate from Purdue University, he was able to think. Today I'm going to show it to you. You can also think, find out a crucial step to integrate reaction and separation. Look at page 2. Methanol, water, methyl acetate. US patent. You see the reaction? Acetic acid, methanol, producing methyl acetate, water. There is an article, 1988. It shows you how to draw the residue curve map for reactive mixture. You can go through a derivation with a reaction. If you have batch distillation vessel, or you have a continuous distillation, total reflux condition, you keep adding heat. The residue, the liquid remaining in the vessel, mole fraction Xi will change. But now we got this reaction. How do we deal with it? Look at page 4. What are the effects of reaction on distillation of VLE? Residue curve map for reactive distillation process. H, molar liquid hold up. How many pound more of liquid stay in the residue? Vapor, that is continuous dynamic process. Vapor coming out as you add heat. Vapor flow rate. What is the mole fraction of no boiling component or ice component in the vapor phase, Yi? Remaining in the residue, Xi. Reaction, mu I, AI, summation. What does that mean? Suppose you have A plus B equals C reaction. Mu A consumption minus 1. Mu B consumption minus 1. Mu C production plus 1. That's what the stoichiometric coefficient. A, B, C. External reaction. You look at next page. The external reaction is I's component, Ni, final number of mole, Ni0, initial number of mole, divided by mu I, like mu A minus 1, mu B minus 1, mu C plus 1. In the reaction, stoichiometric coefficient. That's the definition for external reaction. Now, you go through component, overall mass balance, everything, go through all the detail. Let's summarize the most important conclusion. This come up with two transform coordinate, capital I, xi, yi. Let me use a real example to show you this number, so it makes this real to you. First, methanol, isobutane, MTBE, normal boiling point. The trouble is reactant, product, form an azeotrope at the composition, temperature. Okay? So now, let's look at page 7. A minus 1, B minus 1, C plus 1. The summation is minus 1. Now, on page 6, there's a suggestion. Is the summation here minus 1, less than 0, you can choose the reference component K as a product, in this case MTBE. If this is plus, choose K as reactant. If this is 0, you can choose reactant or product. Okay? So now, in our case, it's minus 1. Minus 1. First, what happened when your reaction, how does it affect residue curve map? On the left, non-reactive system, isobutane minus 619, low boiling species. MTBE 55.1 intermediate boiling point. Methanol and product, there is an azeotrope, 51.2. Low boiling, intermediate boiling, this is a distillation boundary. Dividing the non-reactive system into one region, here, the other region at the top. So, in the lower region, LB, IB, this could be HB1, this be HB2. So, that is 64.7, 51.2 minus, so your RC goes that way. In the distillation column, over here, bottom, bypass intermediate boiling point. In this region, LB, HB, that is RC. On the right, reactive system. So, you notice one thing, azeotrope disappeared. Azeotrope disappeared. The most important feature of reactive distillation, non-ideal mixture, react away or break some of the azeotrope. In this case, if you have reactive distillation, reactant, product, reactant, you will break away or react away azeotrope. That is a major difference. Okay? So now, let's look at our problem. Methyl acetate. Acetic acid, methanol, methyl acetate, water. This is the Eastman process. Given data, pure component. Now the trouble is reactant, product, form azeotrope. Approximately 30% B, 70% C composition. So how do we draw the residue curve map and create a reactive distillation process? Get your pattern. Lee Parton was very young, 25 years old. When the process was in operation, he got his patent. He did not have to do much until now he retired from Eastman. One residue curve map did it. I'll show you can also do it today. So, you have mu A minus 1, mu B minus 1, mu C plus 1, mu D plus 1, consumption, consumption, production, production. Right here, the sum is 0. You can choose either reactant or product, add the reference component K. Let's choose C as reference component K. Now, the key thing about residual curve map for reactive system is you have a transform coordinate capital I could be A, B, C, D. Xi, mole fraction. Xk, in this case, reference component C. Mu I over mu T. Mu I. Mu T summation is 0. Minus 1, minus 1, plus 1, plus 1. 1 minus mu T over mu K, xk. So, for the 4 component, what's the relationship between actual mole fraction and transform coordinate XA? Minus 1 for A, mu T. No, K, this is K, sorry. That's K, okay? Mu I over mu K, mu T over mu K, this is K. So you plug in small xa plus xc. How about B? xb plus xc. C is 0. D. Now, we can only plot a plot using 2 variables. Like a triangle, square diagram. This could be XA, this could be XB. Since this is always positive, this could be 0. We'll use A and B to draw RCM. What is relationship among transform coordinate sum to 1? So now, here comes page 9. Pure component acetic acid. How do we represent that on a transform coordinate system? Let me okay. This is XA equal 1. This is XB equal 1. Pure A, XA is 1, no C. 1. That means on this diagram, acetic acid is here. Why XB, A, both are 0, 0. So, how do you represent that? XA 0, okay? XB equals 0, XA equals 0. So this point is small xa. How about methanol? B, AC, that is 0. B and C, XB, that's 1. So, 0 and 1. 0 and 1. This point is methanol. Okay? HC, product, methyl acetate, XC, that's 1, right? XB plus XC, 1. 1, 1. 1, 1. That is methyl acetate. How about water? D. There's no D here. There's no D here. 0, 0. That is water. So, in this diagram, we have azeotrope between reactant and product. This is high bonding species. So, when you draw residue curve, 53.5, low bonding, 118.1, highest bonding. Water, intermediate bonding. Methanol, intermediate bonding. Methyl acetate, intermediate bonding. So, your residue curve to go from LB, HB, right? LB to HB. On the diagram, you can draw the direction from low bonding to high bonding. So now, here's the challenging part. We are going to use page 10 and 11 to create the reactive distillation process. Okay? First, let's look at page 11. What is going on? First, acetic acid. This is azeotrope. That is this point. Okay? What what does this produce? Methyl acetate product. Here, acetic acid plus water. So, acetic acid input, azetrol, producing acetate. You look at the bottom, acetic acid, you have an azetrol coming in. Azetrol, producing methyl acetate plus HOAC plus alcohol. That is this. All right? Now, how about second part? We have HOAC plus alcohol. You need methanol as input. So, you have two input. You have one input, two input. Producing what? Azetrol plus water. Azetrol plus water. That's how you link the two together. But how do we know it is feasible? What's special about stream flow rate? So, look at page 10. Let's do it. First, acetic acid, azetrol. Acetic acid, azetrol. I do not have a ruler, but I draw, you can draw it. Acetic acid azetrol, right? So, from column 1, we get methyl acetate product plus a mixture. So, mixture of acetic acid and methanol, right? A mixture of acetic acid and methanol must be on this line. Okay, you see here, acetic acid, azetrol, methyl acetate mixture. So, if I draw this column, say, I just pick one point. What's special? 1, 1. This point, acetic acid plus methanol. So, this is what we did, right? That is this. Now, the second one, acetic acid alcohol. Okay? Acetic acid alcohol. You need to add some alcohol to produce aziol and water. You want to produce aziol and water, aziol and water. Here is, you look at our column, acetic acid methanol. No, acetic, yeah, alcohol, that's right, this one. We need some extra alcohol. Need more to this to produce aziol and water. Produce aziol water. Now, here is this is the crucial point to make the process work. If I look at this, at column 2, how much alcohol we should add to make the process feasible? You must have this point. You look at this distance, methanol, this distance, why this point? We need this column to get back to aziol through water, right? So, acetic acid alcohol. This alcohol amount is not arbitrary, right? You notice intersection point? In this distance, we present acetic acid and methanol. But this distance represents additional methanol. You need to add in, right? Now, this is the feasible flow sheet. We have merged two columns into one. This is the reactive distillation column. In the middle part is a packed section. You put the catalyst on top of packing. So, acetic acid plus alcohol produces methyl acetate water. That is the single column reactive distillation. Do you see this? How do you like this? Do you understand what's happening? Now, you can do other example. I have another one on page 12. Eastman loved reactive distillation. They love to file patent, many of them. You will open up the black box of this patent. Here are the components involved. Okay? Water plus methyl acetate producing acetic acid and DME, which is CH3OCH3. That is the reaction. Mu I -1 -2 to 1. Mu T 0 will choose acetic acid and reference component K. So your transform coordinate is this. So you plot XA, XB. Okay? Now, that is on the next page. DME, water. Methyl acetic acid. There is an agent show here. Phi, reactive distillation column. The trouble is low boiling, intermediate boiling, high boiling. This is a distillation boundary. This IB to HB, LB to IB, both are distillation boundary. So the patent said you can have only put what in this region. How? Let's look at one example. Feet. That is the feet. You want to produce direct split. DME 44.68. Distillate. Methyl acetate 143.9. D1B1. So, Phe. This is the direct split. Direct split. How about indirect split? 214.08. High spoiling at bottom. Okay? And you get mixture D2. That is this. So in the pattern, it said your product composition is in this region. That's a pattern. I don't know. Too simple. It's full of people who do not understand RCM. Okay? But they find a pattern together. There are many of them, like this. So, to summarize, this is all Eastman chemical. You have to make sure the additional methanol you add amount is indicated by this line. Your additional alcohol adding in plus acid methanol, okay? Acid methanol, methanol. Make sure it's this point. Then you get to azeotrope water. Azeotrope is this. Tell me what you feel. Creativity. Any comment, any feedback? Later on, you want to solve your own reactive distillation problem, study the paper in more detail, do it yourself, okay? That's it. We will not meet on Friday, we'll meet Monday after the break to help you with the exam.